Alright, well, welcome back to ELE 210 circuit theory. I thought we'd take one last look at superposition. And in doing this look, my intention is to kind of reveal how circuit simulators actually work. So this technique I'm going to show you is not actually superposition, but as a homework problem I'll ask you to solve this circuit using superposition. But let's take a look at a classical way to solve this problem. We have two sources here, and a simple total resistance method isn't going to work. This circuit is so simple that you could actually just apply Thevenin's theorem and take out this load, short these two things. You'd have 2.2K in parallel with 1K to ground, and then you could calculate this open circuit voltage treating this 5 volt cell here and this 2.5 volt cell that's opposing it as a 2.5 volt battery, and you would get a circuit that well, let's just calculate that. So if we wanted to look at this thing from a Thevenin standpoint, we would remove the load, and we would look back in, and we would deaden the power supply. So let's remove the load. And deaden the supplies. In this case, they're both independent sources. Okay, so what we'd wind up with then is we'd have our two terminals here. We'd have, I guess we should give these names, R1 and R2. And we can call this V1 and V2. Alright, so here we would remove the load and deaden the sources. And we would have something that looks like this. Where this is R1 and it's 2.2K. R2 is 1K, and our parallel combinations, so both of these go from this node here to this node here, so they're both in parallel in this calculation, and we have 2.2 times 1 divided by 2.2 plus 1. I'm being a little cavalier by leaving off the k's here. And the answer we get is about 687.5 ohms. We could actually build that if we wanted to. So we now have R Thevenin equals R1 in parallel with R2. That's equal to 2.2K times 1K over 2.2K plus 1K. And so R Thevenin is equal to 687.5 ohms. That's being awfully precise there when we don't really have that privilege. given that these are probably 5% resistors. But at any rate, we know what that is. Now we need to figure out what our source is. So we need to, what we did here was we computed, compute resistance or it could be impedance if we had a complicated circuit. Seen from load terminals. Now, this kind of a circuit here, we could look at this thing and say we've got, well, let's just say, so that's what we're doing up here. So now our next job is to compute the open terminal load voltage. And again, we're just lucky we can do this using Thevenin because the circuit is kind of simplified. But I will do this in a more general way for you to give you an idea how circuit simulators work with circuits of, here we have 2 loops in our circuit, but there's, or actually there's a 3rd loop around the outside. As you begin to connect more components and resistors and transistors and all that sort of thing, you wind up with many loops in your circuit, and that's where a computer can help you solve the circuit. But we'll come to that method in a second. Let's look at computing the open circuit terminal voltage. So now, I'll put the power supplies back in. I've got 5 volts here. And I've got R1 is 2.2K. And then we've got R2 is 1K. And then we've got 2.5 volts here. That's V2. And we'd like to know what the voltage is right here. That's going to be our Thevenin voltage, that open circuit terminal voltage. Well, if you look at this circuit, you've got a complete circuit around here, and it's got 5 volts opposed by 2.5 volts. So, we could draw this thing and kind of draw these as voltage drops, and this 2.5 volts will actually be a voltage drop. And we can look at the current flowing like that. Call that IX, if you will. So, what I've got here is I've got 5 volts is equal to IX times R1, which is 2.2K. So this is a voltage rise because the arrow's coming in the negative and out the positive. All right. Now nothing's going to happen here. This is open. So then I can say that there's going to be another voltage drop here, and that's going to be equal to IX times R2. Sorry, I used the equals there. I meant plus. So here's a voltage drop. This is VR1. Here's a voltage drop. This is VR2. And then because of the way this source is connected, it's actually a voltage drop because the arrow enters the plus and leaves the minus. So we can add in V2. Alright, and so we have and of course this guy is V1. So now we can, sorry about that, glad I looked up. So now we can calculate this thing. 5 volts equals Ix times 2.2K plus Ix times 1K plus 2.5. Well, I can subtract 2.5 from both sides and I get 2.5 volts equals Ix times, factored out here, 2.2K plus 1K is 3.2 K ohms. Okay, and that means that Ix is equal to, bring it back here, Ix is equal to 2.5 volts divided by 3.2 K. We'll do the full thing here. We'll say 3.2 times 10 to the 3, get an answer here, and we get 781.25 microamps, or even though it's not quite proper engineering notation, so you could write this in two ways. You can write it as 781.25 microamps, again being way too specific, and you can also say that's equal to 0.781 approximately milliamps. All right, so we start out with 5 volts at this point, from this node to here. Now we're going to lose some voltage through this 2K resistor, 2.2K resistor. So V Thevenin, I'm going to move this up here a little bit. So V Thevenin is going to equal V1, which is equal to 5 volts, minus VR1. Okay? And we can write that as being equal to 5 volts minus Ix times 2.2K, and that's equal to 5 volts minus 0.781 milliamps, I'm a little out of focus here, sorry, times 2.2K. And so we'll bring back the calculator here, and we'll say that 5 minus the quantity, don't have to do this, but 0.781, now that's, I'm using milliamps, so that's minus 3, times 2.2 plus 3 is K, and enter that, and I get 3.28, not 3.282, 3.28 is good enough for what we're going to do. So we can say that VTH is equal to 3.28 volts, or approximately equal to that. And so we have our TH up here, and we have VTH here. Just gonna make that. And now we can take a look at this from a Thevenin standpoint, and we could say we have VTH is 3.28 volts. And we have RTH is 687.5 ohms. Again, I'm being way too precise here. And we can call this point ground. It's just a matter of a reference point. And now we're going to hook on a 1.5K resistor here. So here's our Thevenin equivalent right here. So this is RL, and that's 1.5K. And so we can do a simple voltage divider calculation here. And we can say that VRL is equal to VTH times 1.5K over, I guess we could write this as K, 0.6875K plus 1.5K. And so that's equal to 3.28 volts times this thing. So let's do that. It's probably time to clear this and go. So 3.28 times 1.5. I'll do the full thing here. You could get away without it, but 1.5 times 10 to the 3 divided by the sum of 687.5 plus 1.5 times 10 to the 3, and I get 2.25 volts if you blur your eyes a little bit. So VRL, and actually let me just, why don't we just use this line right here as our answer line. I'll use some beating this all out. So we get approximately 2.25 volts. Okay, great. We didn't use any other thing but what we've learned. We used Thevenin's theorem. And so, just want to look at